Welcome to section 7.1, part 2. This is the 52nd session of the CISSP exam prep series. This part continues our tour of asymmetric systems, moving past RSA to the other algorithms you need to know. In this session, we'll widen the map of public key algorithms. We'll answer several questions. What is ElGamal and what is its catch? Why does elliptic curve cryptography pack so much strength into a small key? How do two strangers agree on a secret without ever sending it? And how could quantum computing rewrite this entire field? Why does this matter beyond the exam? Because the algorithm you pick shapes performance and future risk. Picture yourself securing a fleet of low-power field sensors that must run for years on a tiny battery. A heavy algorithm drains the power budget fast, while a lean one buys you extra life. And when you architect anything meant to protect data for a decade, you have to ask what tomorrow's computers will be able to break. Knowing these algorithms is how you make those calls with confidence. So what is ElGamal, and what is its catch? ElGamal extends the ideas behind the Diffie-Hellman key exchange into a full public key system that can encrypt and decrypt messages, not just swap keys. When it appeared, one big advantage was that it was placed in the public domain and free to use, at a time when its main rival was still patented. But it carries a real drawback. It roughly doubles the size of whatever it encrypts. That expansion becomes a genuine burden when you need to push large volumes of encrypted data across a network. Free to use, but heavy on the wire. Why does elliptic curve cryptography pack so much strength into a small key? Elliptic curve cryptography, or ECC, builds its security on the math of points on a curve. You can add 2 points, and you can multiply a point by an integer to land on another point. The trap is the reverse. Even when you know the starting point and the ending point, recovering that hidden integer multiplier is extraordinarily hard. This is the elliptic curve discrete logarithm problem, and experts believe it is tougher than the factoring problem RSA relies on. The payoff is efficiency. A short elliptic curve key delivers the same protection as a much longer RSA key, which is exactly why it shines in constrained, low-power devices. How do two strangers agree on a secret without ever sending it? That is the magic of Diffie-Hellman key exchange. Two people who share nothing can end up holding the identical secret value, yet that secret never travels across the wire. They publicly agree on a couple of large numbers to start. Each one then picks a private random number and combines it with the shared numbers to produce a value they can safely send. When each side folds the other's value into their own private number, both arrive at the same result. One caution for the exam. Diffie-Hellman is a key exchange method, not an encryption algorithm on its own. It is the classic way to establish a shared symmetric key, and it appears throughout modern transport security in its ephemeral forms. How could quantum computing rewrite this entire field? Quantum computing swaps the ordinary 1 and 0 bits for quantum bits, or qubits, that behave in richer ways. It is still an emerging research area with no practical machine yet built, but if a genuinely powerful quantum computer arrives, it could solve problems that stump every classical computer. That includes the very factoring and logarithm problems that RSA and Diffie-Hellman depend on, which would render them insecure overnight. The same technology could also power new, tougher algorithms. Researchers have already built lab versions of quantum key distribution, a quantum way to establish a shared secret, though it too remains experimental. What should you do about the quantum threat right now? Think in terms of shelf life. Assume an attacker may quietly copy your encrypted data today and simply wait, holding it until future quantum tools can crack it open. If that data will still be sensitive by then, the exposure is already yours to manage. There is a second, sobering angle. The first practical break of modern cryptography may never be announced because whoever finds it gains the most by keeping it hidden and using it in secret. So plan today for a post-quantum world and weigh how long each secret truly needs to stay protected. So let's bring it together. ElGamal extends Diffie-Hellman into full encryption but doubles message size. Elliptic curve cryptography leans on the hardness of its discrete logarithm problem to deliver strong protection in short keys. Diffie-Hellman lets two strangers agree on a shared secret without ever transmitting it, and it is a key exchange, not encryption. Quantum computing could someday break today's asymmetric systems, so judge how long your data must stay safe. Carry these algorithms forward, and you can match the right tool to each real-world constraint. The MCQs covering all the topics and concepts from this session are available on rucloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.